So to start understanding what is really the fundamental operation that happens inside those convolutional neural networks, let me just start with a simple problem. And this problem goes as follows. I have somewhere in this kind of time axis a signal. This is the duration of this signal, and the shape of the signal is not really important, but what is really important is the assumption that I do know the shape of that signal. And let's assume that I have, let's say, call this signal x of t, and ask you the question as to can we come up with a method that we can sort of provide the location of that signal, whereabout in this buffer, let's say, of the signal is located. Okay, so a simple kind of approach that we can think of is the following. Since we know the shape of this kind of signal, I can actually start at the beginning of this buffer at this location, let's say 0. And for every position, if you like, the hypothesis, that the buffer is, the signal is located at this specific point, and start making an operation that will effectively means taking the dot product between the contents of that buffer and that signal, and this means that multiplying every element of this buffer with the amplitude, let's say the amplitude was 1 of the signal, and summing over all of the elements. And so if we do that, then it's a whole bunch of zeros times 1, then we will be getting a result that it will be 0, evidently. Okay, so that is the 0. So we'll be getting, in fact, all zeros results up to the point where we start having my hypothetical kind of signal be right at the location of that true location of that kind of signal. So after this point, as you can understand, we're going to have some overlap between this signal and this. So we'll be starting getting some non-zero results out of this kind of operation. And right where exactly the signal is located, right under it, then we will start getting a peak. And then evidently we'll start, going back to 0, and so on and so on. So this is basically an approach. If we take the argmax of what this kind of operation, this will be, let's say, the tau, the location that sort of indicates the that we have predicted as far as this kind of signal is concerned. So what we just did is an example of what we call a one-dimensional correlation operation, or cross-correlation operation, because we are trying to correlate a hypothetical signal located in this hypothesis over here against some other signal, the x of t. So I will actually call this simplistically, let's say, y of t. I'm actually correlating x of t and y of t, and this kind of correlation operation is able to retrieve for me in this simple single dimensional kind of space the location of x of t. And this is exactly what is being done in a kind of a two-dimensional and three-dimensional kind of space inside a convolutional kind of neural network. In fact, now what we will do is we will expand into another example of where we have now this taxi image, and we try to understand how we will be able to detect the presence of that kind of taxi in that image. But before we go there, I wanted to actually share with you some details in our site where we have, if you like, a numerical example. Confusingly, the true sort of operation of what is actually called convolution is implemented inside the PyTorch, TensorFlows, and so on, all these kind of machine learning frameworks as correlation operations. And with the exception that we actually flip in the time domain that signal y of t we are, the two operations, as it is actually clearly shown in your site later on, the two operations of convolution and cross correlation result into identical results. And for the purposes of our purposes, from a pure implementation efficiency kind of perspective, we always prefer to refer to implement them as cross correlation, despite the fact that we are refer to them as convolution operations. So let me go into the following kind of discussion now, where we are going back to that kind of a taxi image. Let me just write over here if I kind of try to squeeze it. So this is our image that we have seen earlier with this yellow cab in the middle. And here I have right in the middle kind of a taxi. Okay, so all right, and I ask you exactly the same question: how we can potentially detect this kind of taxi in this kind of image. Okay, all right, and maybe the I mean, if we had known the exact shape of this object, like we have assumed earlier, then the operation actually would be straightforward. We'll take this template again. We'll call it Y now, and we will start sliding this kind of template across this kind of image to be able to, and at some point where the template is exactly present right on top of that object in the image X, we will then declare that that's basically the location of that object. The problem, however, is that in this kind of approach, we have first assumed that we will know exactly the shape of that object, which is not realistic, because the object is definitely going to vary quite a lot. Let's say the object may be rotated, translated in sort of or being sort of because of the lighting condition, maybe not sort of very evident its exact shape. It's shadowed, for example, or occluded by other objects. And the other assumption is that in terms of computational efficiency, the larger our kind of prototype is in terms of number of pixels, the more expensive this kind of operation becomes. So in order to solve these two problems, what we will do, what we would suggest is we will not abandon this kind of sliding operation that we will call cross correlation a bit earlier, but if in fact what we will actually do now is we'll use a much smaller prototype, and we are now face the problem as to what is really the contents of that sort of prototype that we will be calling from now on a kernel. So let me just draw the kernel over here, and maybe I can start answering the question as to what should be the contents of this kernel that will be able to detect this cab over here. All right, so this image is extremely simple. In fact, it has zeros in these pixels, and all the other pixels which we have not drawn anything are 255. So 255 corresponds to pure white, and 0 corresponds to black. So since I have a black and white image, I can suggest that maybe if I can have a kernel whose pixels, so this is a kernel which is, the size of that is not necessarily accidental, it's 3 by 3 in this case. And if I locate over here in these pixels, I made them, let's say, zeros, and over here I made them 255, then you can all understand that as I'm sliding around this kind of kernel, I will definitely go and at some point hit this location over here with this kernel, and at that moment in that location, then I will be getting some definitely a significant peak if I may call it like that, out of my cross-correlation operation. So we'll see the details, the mathematical details of that cross-correlation operation shortly, but that's basically what is going to happen then. And so exactly the same thing will actually happen in this location and potentially in this type of locations and so on. But I don't think that we have the complete story yet, because I can suggest an additional kind of kernel. Again, it will be 3 by 3. And this kernel, if it is sort of programmed to contain this type of information, where now the black pixels are like this and the whites are over there, they're kind of diagonally, then we will be able to pick up probably this feature over here, where the windscreen is, and so on and so on. So we can actually suggest other kernels as well, where we now have the other diagonal. These wheels can be detected by having something else, some other kind of kernel, where maybe these guys will be need to be sort of colored like this, colored in quotes, or programmed like this with 255 and zeros. And as you can understand, all of these kernels, if they are positioned at some point in this kind of image, and I'll be calling now from now on this aggregation of kernels as a filter. So filter for me will be this kind of a three-dimensional structure that it will have 3 by 3, let's say, spatial coordinates. So this is the 3 by 3 spatial, let me call it extent. And it would have some kind of a depth, D. And this depth, let's write it, depth is, of course, the number of kernels that I employ in this filter. Okay, so over here, that is basically a structure that I will see that it will be a fairly, I would call it useful for me to be able to detect now features from images. Okay, and now let's see the mathematical description of what we have just described. Let me go back to the site. And in that site, we have the so-called two-dimensional, the extension of the so-called two-dimensional cross-correlation operation. And it's exactly shown here in this kind of image, in this picture. So we have an input image of 3 by 4 pixels, and we have a kernel of 2 by 2 in this case. And the kernel is going to be positioned in all possible locations in this image, in this input image. So in this specific case, it is positioned at this moment in time at this location over here. And we are going to be forming the dot product between the kernel and the input image. And evidently the dot product is A times W plus B times X plus E times Y plus F times Z. And that will actually be a scalar that it will give us the feature value, extracted feature value out of that operation. And we will do exactly the same thing over and over again. We're going to slide the kernel into another location, BCFG, we'll do the dot product, CDGH, another dot product with it. And to cut a long story short, we are going to be getting a 2 by 3 output image. And from now on, we'll be calling this output images, input and output images feature maps, because they are mapping the features that we have extracted with the usage of kernels. Here we see just a single kernel, but in general, we're going to have multiple kernels be involved in the shape and form of filters in these operations. And so basically, this is what we will be doing from now on, and we will be sort of need to discuss next some architectural elements of that are sort of encompassing this operation over here, but also enhance it with further correlation type of structures inside convolutional neural networks.